Hello everyone. Today we will start another topic, that is steam nozzle. It is a passage of uniformly varying cross section in which velocity, that is kinetic energy of the fluid, increases in expense of its pressure energy. So as per the definition we can see here, it is used for turbines, jet engines, rockets, injectors, etc. So wherever we need more amount of the velocity or kinetic energy, wherever we want to increase the kinetic energy of the fluid, at that places steam nozzles or nozzles are used. Let's see a simple schematic of the nozzle. So here you can see gradually varying cross section is there. So here is the inlet and this is the exit. Let's say inlet conditions are P0, V0 and C0, that means pressure, volume and velocity, and at exit P1, V1 and C1, pressure, velocity and volume and velocity. Here you can see we, instead of denoting velocity with the V, we are denoting it with the C. This fluid is a gaseous in form. Volume also takes part in a calculation. So to avoid the confusion between volume and the velocity, we are denoting volume by V and velocity by C. Here in nozzle, we want that pressure energy to be completely converted into kinetic energy so that we will get more and more amount of the velocity at the exit. That's why these nozzles are kept insulated so that the heat will not be transferred into this nozzle or from this nozzle. Hence the process is kept adiabatic in nature. So the process for the nozzle, let's say this is the inlet condition 0 and this is the exit condition 1. The process for the equation for this process is PV raised to n equal to constant, that is adiabatic equation. Here Q is equal to 0. Now let's consider 1 kg of mass is flowing through the nozzle. And apply the steady flow energy equation for this system. So here we can see that energy at the inlet should be equal to the total energy at the exit. So enthalpy at the inlet plus kinetic energy at inlet plus the level difference at inlet, and as we are seeing whatever the energy, heat energy over here, that heat energy, this should be equal to the exit total energy, that will be equal to enthalpy plus kinetic energy plus level difference plus whatever the work transfer has been done. Now as we have seen here, we have made this system insulated or made it adiabatic. So Q will be equal to 0 as it is an adiabatic process. Also work transfer is also equal to 0. External work transfer, we are not providing any external work for this conversion, hence external work transfer is also equal to 0. Now let's also this is at the same level, so Z1 equal to Z2. Now let's rearrange the equation by putting all these values over here. We will get H0 plus C0 square by 2 equal to H1 plus C1 square by 2. If we rearrange this equation for the velocity C1, that means how much energy, how much velocity you are getting at the outlet, so we will get C1 is equal to under root of twice H0 minus H1 plus C0 square. Here enthalpy should be in joule per kg, then and only then you will get velocity in meter per second. Another thing about this nozzle is that these are the steam nozzle, that means this is the inlet, that is the steam is coming from the boiler, and when it is coming from the boiler, pressure of that steam is very high, that means velocity is almost negligible. So we can write this C0 is it is almost equal to 0. So we can modify this or simplify this equation with C1 is equal to under root of twice H0 minus H1. As this enthalpy we are taking it from the steam table, it is given in the in a kilojoule per kg. So we can write it as C1 equal to under root of 2 into 1000 H0 minus H1. And we can write it as 44.7 under root of H0 minus H1. If we are taking H in kilojoule per kg, then for C in meter per second we have to use the formula, that is 44.7 under root of H0 minus H1. Now let's see effect of friction and the nozzle efficiency. Ideally, when the nozzle is designed, it is designed in such a way that the process inside it will be an adiabatic process, and it should be isentropic process, that is frictionless process, so that there will be no heat generation inside it, and maximum conversion of the pressure energy into kinetic energy will be there. So if we draw a TS diagram for it, TS, these are, let's say these are the pressure lines. So this is the initial condition P0, this is exit condition P1. So ideally when it is designed, it is expected that it should follow this process from 0 to 1 dash, but practically it is not possible. So instead of following the 0 to 1 dash, it will follow 0 to 1. Reason for this is, first one, due to wall friction, and second one is a fluid friction. When the fluid flows through the nozzle, these walls, it is expected that it should be smooth, but practically it is not possible when it was manufactured. At that time, the surface inside this nozzle, it can be slightly rough. So due to that, there will be a friction between these walls and the particles of the fluid. So due to that, there will be generation of the heat, and hence instead of getting the isentropic process we will get this type of actual process. Also, fluid friction, that means the particles of that fluid will collide with each other, and due to that again there will be a chances of heat generation which again creates a loss in a conversion of a energy, and we will get this actual process. Now, instead of getting the enthalpy change from H0 to H1 dash, we are getting H0 to H1. So we can write here nozzle efficiency, that is actual enthalpy drop to isentropic enthalpy drop. So this will be equal to actual enthalpy drop is from H0 to H1, and isentropic enthalpy drop is from H0 to H1 dash. So this is how we can find the nozzle efficiency. Now let's see types of nozzle. First one is a convergent nozzle and second one is a convergent divergent nozzle. Let's draw the schematic for this. Convergent nozzle is having the uniformly decreasing cross-section area, while convergent divergent nozzle is having initially decreasing cross-section area, then there is a throttle part, this throttle part, and again increasing area, that is a divergent area. This convergent nozzle is connected to a chamber, and after that chamber there is a wall. So initially the pressure is P0, that is the stagnation pressure, 0, that means velocity is almost 0. Now it is observed that in a convergent nozzle, when the fluid is passing through this gradually decreasing area, the velocity will start increasing. So let's say here is the P0 condition. Here is the P0 condition. Now if we keep this wall completely closed, pressure here and here, it will be same, so there will be no flow of the fluid. At that condition the pressure will remain constant. When we allow this wall to slightly open, the flow will start, and this pressure PB, that is back pressure PB, will drop down little bit. Let's say here it has dropped down to this one, let's say PB1. So here what will happen, this P0 pressure will drop till it reaches this PB. When it is dropping down, there will be you will observe the flow of the fluid, that means increase in the velocity. Now let's say again, if we open this valve further, you will observe it is reaching to another pressure, let's say PB2. So again the flow will increase and the pressure will drop down from P0 to PB2. If we allow this valve to open further, the maximum condition, the flow or the velocity will reach to the sonic pressure, sonic velocity. That means, let's say this is the pressure, back pressure PB, where you will get the sonic velocity. That means it will drop down from P0 to PB, and when it is dropping from P0 to PB, at this condition the velocity or velocity at the exit of this nozzle will be the sonic velocity. That means Mach number will be equal to 1. Now even if we allow this valve to open further in this type of nozzle, you can't observe the further increase in the velocity. That means maximum velocity you can obtain here is the sonic velocity. So this type of nozzle is used only where you will need the velocity up to sonic velocity. Whenever you want the velocity to increase beyond the sonic velocity, or we can say Mach number more than 1, at that time convergent divergent nozzle is used. Once you have reached to the sonic velocity, there will be the constant mass flow rate. That means even if you allow this valve to open further, it will provide you the same mass flow rate. That condition is known as the choking. So you can see here, if we draw a graph, another graph of mass flow rate versus PV. So here is the initial PV, that means P0. Okay, so gradually when you are opening this valve, gradually there will be increase in the mass flow rate and you are decreasing the PV. So gradually there will be increase in the mass flow rate. But when it reaches to the sonic velocity, so here is a critical PV. Okay, so we can see that it is a critical back pressure. After this, even if you allow the valve to open further, there will be no change in the mass flow rate and you will get the constant mass flow rate. So this condition is known as a choking. Hence, wherever you will need the velocity more than the sonic velocity, convergent divergent nozzles are used. Let's again extend this system by providing a chamber over here with a valve like this, and let's draw a graph of pressure versus the length. So here is the length, here is the pressure, and here is the throttle condition. So this is throttle. Now again here, if we are keeping this valve completely closed, P0, here inlet condition is P0, so exit condition will also be P0, and we will observe the constant pressure. And as the pressure is constant, there will be no change in the velocity. That means there will be no flow of the fluid. Once the valve will be open slightly, the pressure will drop to, let's say, somewhere here, that is PB1. Now when it will drop to PB1, what happens inside this nozzle is, here in a convergent section the pressure will drop down, and in a divergent section it will again increase slightly so that it will reach to this pressure, back pressure PB. If we allow this valve to open further and let's say PB2, again in a convergent section the pressure will drop down, and again in a divergent section it will increase so that it will reach to back pressure PB2. Further, if we allow this valve to open, let's say PB3, and let's say here in a convergent section it will reach to this maximum condition, that is sonic velocity. Once it will reach to sonic velocity, again as this pressure is above this condition, it will again go back so that it will reach to PB3. Okay, now let's say someone would have told you that there is another back pressure where this will be continuously going instead of increasing, it will be continuously decreasing. So let's say, let me draw. So let's say it will be like this. So this is something known back pressure. PB. That means what is going to happen, this pressure P0 will continuously decrease to PB. As it is going to continuously decrease to PB, what will happen? Here you have already reached to the sonic velocity. As the pressure is, you are allowing the pressure to decrease further, that means its velocity will go beyond the sonic velocity. That means you will get the Mach number more than 1. So it will reach in the supersonic velocity zone. Now what happens if the pressure is not this one, it's above here? So here let's say PB 4. So what will happen here if the pressure is something like this? In a convergent section, the pressure will drop till it reaches the sonic velocity, and further again it will reach over here, and once it will reach somewhere here, to catch up this pressure it will suddenly increase and you will observe a shock waves, so which is again not feasible. Similarly, if the pressure is below this known pressure, where you will get a supersonic velocity, so PB5, again it will reach somewhere here, and to catch up this pressure suddenly you will observe a shock over here. So when we are designing the nozzle, it is very important that this pressure should be known to us, and the nozzle should be designed as per that pressure. So this is what happens in the convergent divergent nozzle. So as we know very well that in a convergent section, pressure decreases and velocity increases, while in a divergent section pressure increases and velocity decreases. But when we combine, we will observe the unique performance, that is pressure will further decrease beyond the sonic condition, and you will get the supersonic zone. Thank you.